All right. Okay, so it's our second to last day together. Last week of school with the semesters, kind of exciting. Before I get started with talking about math, I'll just say there's a homework assignment. This is just like stuff that's been on the announcements, but I'd like to say it that there is going to be there's an assignment that's due technically on Thursday, tomorrow night, but it's really just going to be due. Think of it due on Sunday. Just university policy that I can't have it actually due on Sunday, but I will only have office hours. I will have office hours, tonight and tomorrow night. And those are the two nights that you'll be able to ask me about how it works in office hours before the assignment's done. Okay, and then I'll have office hours all next week, like the normal times up until the final exam. And then I made one of those big long packets so you can go through in previous exams and find, if you want to do a divergence theorem question, you can find where to do questions like that. Now, in the past, there are lots of different kinds of notation that people use for different, for certain flux integrals, work integrals, whatever that be. So I've made a little, like a little Rosetta Stone, a little translator for what other classes in the past have used and what notation that we've used. So for example, like you might see something like v dot t ds over c. Sometimes people write an integral like that. And you're like, what the heck is that circle right there? That circle is just there to tell you that C is a closed curve, for example. It's a loop. So lots of weird notation that I just thought I'd tell you. Another weird thing is some people, instead of writing curl of V, they'll write this del cross V, which is kind of an abusive notation, but it kind of helps make sense when you think of del as this partial x, partial y, partial z. It it kind of also makes sense because it notationally makes sense, but it doesn't. It's technically an abusive notation because then you also can write the divergence of V in that way is like del dot V. But I've written all this in the packet, so you can see if you want to do some questions, and you can kind of see if there's something that you don't recognize. Let me think. Any other things I like to say? I don't think so. So I'll say that we've actually covered every single topic that will be on the midterm exam. So we're ahead of most other classes, which is a good thing. And so I'd like to actually take a moment to pause and just sort of acknowledge that there's been in these past few weeks, we've learned how to do a lot of different things. We've learned how to do all these different kinds of vector integrals, which is, on one hand, we learned how to do all these vector integrals. On the other hand, we learned these fundamental theorems, which give us alternative ways to do these vector integrals. So there's so much floating around that I want to actually just come back to earth and just do just look at loose ends and reminders and look at some pointers. So okay, here's going to be some loose ends or reminders or pointers about vector calculus. So I'm going to be repeating a lot of things that I said, but I just want everything in your brain to feel pretty concrete with all of this stuff, because it is difficult. And let me be totally honest, when I was taking this class, by the time we got to this section, I had absolutely zero idea what was going on. And I just symbolically knew what Stokes theorem said and the divergence theorem said. I didn't really know how to compute anything. And that was kind of in that class, there was not nearly enough time dedicated at the end to do these fundamental theorems of calculus. We've had so much time to do it, but I remember just being totally lost. So here are some things that I think would have helped me understand things. So let's just categorize. There are two types of vector integrals that we know how to do. That we've learned, okay? The first one is circulation integrals. So we've learned how to do an integral over C, where we've taken the vector field and we've dotted it with the unit tangent vector we've done arc, and we've integrated that over the length, the ds of the thing. Okay, so here C is an oriented curve. It could be in 3D, in 2D, or 3D. Both of these make sense. And at this point, I hope that if I drew something like a vector field, this was V, and I drew some curve C like this, I hope you have enough intuition for what this integral is that you could probably like eyeball it and say, this is probably positive. I hope you have enough intuition for what the thing on the left is to guesstimate the sign or kind of see what kind of information it's recording. It's how much you're working against a vector field. Okay. So that's only one of two types of integrals we've learned how to do. The second type is, so this is one. The second type that we've learned is we've learned how to compute the following kinds of integral. So it's a double integral over a surface where we've taken a vector field and we've dotted it with the normal vector over the surface. And we've done this with respect to area. So S is definitely an oriented surface, and that's in 3D. And the picture is, of course, something like the following. So you really have to imagine my vectors V, they're definitely in 3 space now. So something like this. So to emphasize, I'll draw X, Y, Z in the corner so you know I'm a surface, 3D. And your surface might look something like this, okay? And here is the outward normal vector. And across the surface, you take the dot product of the vector with the normal, and you can get, I hope you'd be able to sort of eyeball in certain situations, maybe the sign of what this thing measures if you just drew it out geometrically. So these are really the two kinds of integrals that we know how to do. And I know you might be like, maybe this is boring to you, maybe it's not, I don't know. So this is a work or circulation integral, or sometimes people call it like a vector line integral. And this is down here, this is a flux integral, or sometimes people call it a vector surface integral. Okay, so I'm just gonna copy this right here, and I'm gonna move on to the next page. And maybe you're like, this is super boring, I know this already, or maybe not, I don't know, but let me show you. Okay, paste. I'm pasting that last one. Paste. What? Sorry, hang on. Zoom? No, I don't want zoom. No. Oh, what the heck? Hang on. Maybe I didn't actually copy it. Sorry. Maybe two types of integrals we've learned. Let me copy this. So copy, moves it. Okay, now it's copying. Sorry about that. There we go. All right. Okay. So let me show you two kinds of non-examples. I remember it was like, I kind of got, this is something that once I realized, it was very illustrative for me. So here are non-examples of integrals just that don't make sense. So here's why you'll never see a double integral over a surface. I'm taking a V with some sort of tangent vector, dA. This is not something that would make sense, really, because let's just think about this. This would mean we've got some surface S, and we've got some vector field in 3D space, so this is V. And then at every point, what would we be dotting? What would this try to tell us? We would try to be dotting at each point the vector V with a tangent vector. What would T be? We have so many of those. We have like an infinite choice of them. Even if we restrict to unit ones, we have a whole, like an infinite family of tangent vectors. So that's not really well defined. Like if I wanted to make sense of this integral, what I'd have to do is at each point, like specify what a tangent vector would be, which I don't have to do in the normal case, because at each point, I'm gonna zoom in for a second. At each point, it's very clear what the normal would be. There's like only one choice of normal. Okay, I'm lying, there's a second choice, but I'll tell you if it's the positive or negative. And so a normal to a surface is really easily defined, but a tangent to a surface is not easily defined. For that reason, you'll never see this symbol right here. Another thing you won't see, and I hope this is helpful for some people, because I know once I realized this, it helped me straighten things out a lot in my head. Another thing you won't see is the integral over a curve in 3D, where you've taken v dotted with a normal against the curve, ds. Here's why this wouldn't make sense. Let me draw a curve C. It's in 3D. That's my C. And, I've got some vector field v. But at each point, what would my normal vector be? Again, I have like a whole slew of options, and it's not quite clear. It's not so well defined which one would be the normal vector that I would dot with. Here's a whole collection of normal vectors to the tangent vector. And I'll do the tangent vector. I'm going to zoom in for a second. It's very clear at this point what t is. T is this one coming straight out, okay, or it's that one coming back there. We've got two options, but so these are t's, but normal vectors, there just wouldn't be too many, and I would have to specify which normal I was talking about. So for that reason, we're not going to see something like that ever come up. Now, something that we've actually I'm skipping teaching that actually doesn't really, I looked at exams in past years and this has actually never come up, but something I learned when I was a student was you can, if C is in 2D, is a 2D curve in the XY plane, then you actually can define a normal. So you can, at each point, and this is because in 2D there's a lot less dimension than in 3D, you can define, I'll zoom in, this would be a tangent vector, and this would be a normal vector. And there's really only one choice, or at least one in its opposite choice, that you can do. So in 2D, you actually can make sense of the single integral over C v dot n ds, but I've repressed teaching this because we didn't have enough time, and I just thought, and other instructors are not doing it. I think other instructors just like barely finished parameterizing surfaces recently. I think, or maybe at the end of last week. So we're pretty ahead. But this is, so in theory, this is something that you could do. I thought I'd mention it, but I hope this is, if this was all boring to you, I'm sorry, but I hope non-examples are illustrative of something that you won't see in this class. So that was my little plug. I had a discussion of this in office hours last night, and I thought that it was helpful for students there, and then it was also helpful for me, I remember. Okay, so I'm going to keep on reviewing. This was page 2. We're still just like talking about vector calculus right now, just computing stuff. So you might, another thing that has confused people, and I remember something that totally confused me, and this took me actually kind of a couple years to really solidify in my own brain, but here are two kinds of flux integrals. Here are two types of, computationally, these things are mechanically flux integrals, or these are vector surface integrals that we've seen. Okay, so I'm gonna go to this page. So two of these blue kinds where we've integrated a vector field, we've dotted it with a normal over a surface. Okay, so let me, on one hand, we've done just basic v dot n dA, okay? You're like, what? Okay, and then the other one is the double integral where we've taken the curl of v, then we've dotted it with n dA over some surface S. Okay, so these are computationally the same things you would, okay, what am I trying to say? These are both of the form, you're taking some W and you're dotting it with an N dA. They're both of this form. But they're both telling you geometrically is kind of different things. So let's talk about these two. So these, while both technically are flux or vector surface integrals, they tell us different ways how V geometrically interacts with the surface S. Okay, so on the left, this is telling us this is a number. This is some number if we actually computed it. And what does that number describe? That number is describing us how much the vector field V is flowing through the surface of N. So this number, this integral, be that 5, be that negative 22, be that whatever the heck that number is, this integral tells us how much V is flowing through surface S. Okay, cool. This was now on the right-hand side, and I'm sorry this is boring some people, but I remember being confused when I was at this point, so I hope this is helpful. This is telling us something geometrically that's different. So this is telling us, this number tells us how much counterclockwise, let me do this, let me erase, I want to kind of change that. How much V is rotating, how much V's rotation lands on S. Okay, so that's really telling us two quite different pieces of information. So and this, on this side, this quantity is highly related to the triple integral of divergence. So this blue thing is related to the triple integral of divergence of V dV over a region omega, where omega is bounded by S. Whereas on the right-hand side, this flux integral, this double integral, is related to a single integral of V dot t over the boundary ds. So this is via divergence theorem, and this is via Stokes theorem. And so, like, you can see the left-hand column is quite different than the right-hand column in terms of how you're really intuitively understanding these pieces. Yet, if you ever sat down to compute something like the double integral of 0, 16x, 4y squared, I just literally just made that up. Oh, is it frozen? Oh, I'm frozen. Sorry, everybody. Sorry. Stop mirroring. Start mirroring. Okay, so all that's changed is down here. This is what you probably didn't see. That was, so what I was saying is, say you did do some integral dA over some surface S. Like, if you just enter this into a computer, look, it's a flux integral. The computer's not going to care or know if this was this V or was this curl of V. So that's what I'm saying, that computationally, you're going to compute these numbers the same way. But in your head, you've got to know if you're talking about like swirly, rotation-y stuff, like in the right-hand column, or if that's telling you fluxy through divergency stuff. So that was kind of something I wanted to say. So I'll color that in green, so it's kind of like the computer doesn't know if it's the left column or the right column. Okay. Okay, so I hope this isn't boring. I hope this is helpful. So let me, okay. So that was kind of all the recap I wanted to do. Now I just want to keep on doing examples. Okay, so we ended with divergence theorem. So on Monday, I want to keep doing a little bit more divergence theorem. I think we've had a lot more practice with Stokes theorem. So let me just do a couple more examples with divergence. So here's an example, divergence theorem. Okay, so I'm going to say compute the double integral. Okay, so compute the flux integral. So V dot N dA over S. So immediately I'm looking at, like, I'm going to pause. I haven't even told you what V or S or N are. I'm going to go to the previous page and say that we're in this left column. Okay, so we're kind of thinking about how much v is moving through S. So we might be thinking about divergence. That's kind of where our brains are. And I'm going to tell you v is 0, 0, z cubed. And then S is the parabolic bowl given by z equals 1 minus x squared minus y squared, where z is greater than or equal to 0 and n is upward, normal, upward or outward. So the picture is this. I've got this thing. I'll do the surface in purple. So that's the base, and it's the upside down wine glass. So that's S, and that's N. And if I draw the vector field, well, I know it just has z component. It's just going to be a vertical vector, and I know it's actually always going to be pointing up, at least in the positive. When z is positive, z cubed is positive. So I know that it starts getting really big up here. So that's going to be n. That's going to be v. That's my picture. Okay. So the thing is, if we really want to compute this by hand, okay, I'll write this down. So to do this integral by hand or by scratch, we'd need to, okay, parameterize S. That's going to be a pain in the ass. Then we'd have to compute partial U, partial V. We have to compute the cross product, and then and only then we could do an integral. Okay, so that's a lot of time. I'm gonna show you divergence theorem can be a way to skip lots of that work. So instead, use the divergence theorem. The divergence theorem basically says what comes in must go out, or kind of basically something like that. So what I'd like to do is so if you notice the surface that we have right here, unfortunately, it's not a closed surface. So think about it for a minute. Maybe it's obvious to you, maybe it's not. Remember, a surface is closed if it cuts off a solid region. So maybe you're thinking about the solid region it might cut off, but there's an important face that's missing. So think about what face that might be. Wait like 5 seconds. It's a face that's missing. Face is the bottom face. You're missing the bottom face. So unfortunately, S doesn't really bound that nice interior chunk completely, but I'll write this. I'm going to let S1 be the unit disk in the z equals 0 plane. I'm going to let N1 be the downward pointing unit normal. So I'm going to zoom into my picture right now. I'm going to show you what I mean. So I'm zooming in up here, and I'll do it in this peach color. So on the bottom, that surface on the bottom is S1, and its unit normal points down. So that's N1. Okay. So N1 is the downward pointing unit normal. And now S and S1 together close something. So now I can use the divergence theorem. So now we'll say, now that the boundary of the boundary of omega, where omega is that 3D internal part. So omega is 3D inside. It's a solid region. Remember, S and S1 are 2D things. Omega is a solid. So the boundary of the solid is equal to basically S plus S1. Thus, divergence theorem says that the triple integral over omega of the divergence of V is going to equal a sum of two flux integrals, flux through the top plus flux through the bottom. V dot N over S dA plus the integral over S1 v dot N1 dA. Okay, so that's what Stokes' theorem sets up for us. I'll highlight that. And the important piece, the question that they're asking for, this middle one, that's the thing we want to compute. And the idea is the thing on the left and the thing on the right are probably easier to compute. So in fact, let's just think about this for a second. It's important that I'm considering it, but I'll show you that it's actually 0. It's actually 0 because V along the z equals 0 plane is, I'll fill it in, 0, 0, 0 cubed, and that's just 0. So along the bottom, the vector field 0. So in fact, there's like this piece. So this piece equals 0. And so I'm going to copy and paste just this. Okay, copy. I'm going to move to this next page. So let me see. I'll try to copy. Okay, I'm going to bring some other stuff. So okay, so we've got this, and I'll go over to the left side, and I'll copy and paste this information. Okay. So you can have this. Okay. Okay, so this is all the data we need. So now, and you can see I erased this piece over here. So now I'm just going to compute the left-hand side. The left-hand side is going to be doable, and we don't have to do all the crazy parameterization. So first, what we've got to do is compute the divergence, but that's not so bad. So number 1, compute divergence. Well, this isn't so bad. So remember, you take an x derivative of the x component plus y derivative of the y component plus z derivative of the z component. So that means I'm going to get the divergence of v is, okay, I'll be really explicit, partial 0 partial x plus partial y 0 plus partial z cubed. We're going to get 0 plus 3z squared. So my divergence is 3z squared. Okay, that's not that bad of a function. So I've got to integrate that function over that region. That function over that solid region. And this is why we had midterm 2. Because midterm 2, we had all sorts of practice by integrating functions over 3D regions. That's basically one of the big reasons why we computed, but why we did some of that. So now we've got to do, so now we have to compute the triple integral of 3z squared dv. Okay, so I'm thinking which coordinate system do I want to use? Probably cylindrical, right? We've got rotational symmetry. So let's define, so use cylindrical. To do this, we'll look in the RZ plane, and the RZ plane is a half plane. So here's R, here's Z, and now I've got this parabolic bowl. So that's saying, and the parabolic bowl ends at 1. These things are both 1. So I can say R goes between 0 and 1. And Z, so now those are horizontal strips. This is my minimum horizontal strip. This is my maximum horizontal strip at 1 and 1. And for 1 in between, my Z max is up here, and my Z min is down there. Z max, Z min. So Z, we can see the lower bound Z min is 0, and Z max is, I'll highlight where it appears. It appears at this thing. This is Z equals 1 minus R squared, so that's the maximum value. So Z is equal to 1 minus R squared, and we should have theta going from 0 to 2 pi. And so we're going to set the full thing up. The full thing is equal to the integral from 0 to 2 pi. The integral, and that's going to give us a d theta. Then we'll have z going from 0 to 1 minus r squared. That gives us dz. And then 0 to, oh, hang on. Oops. I told you I make this, so I got to flip that. Oops. See why that was bad of me? I should not have done that. I should have been smarter, because this has a constant in it, so it better be innermost. So 0 to 1, and that means I've got to fix this. I've got to put that there, and this is dr. Okay. Then I need my function. So I really like this highlight feature. I wish I had learned of it sooner. So that comes from here. That's my f. But then I'm missing one crucial piece, and that is this is not dv. I need to slap an r on it. So I need r. Now that thing is dv, and we are in business. So that piece is this piece, and this is the integral to compute. And I think that this is an easier one to do for everybody than having to parameterize the thing. I did it on my own, and I got pi over 2. And that makes it makes sense that we're integrating a positive thing. We get a positive number because we integrated a function that's certainly always positive. So that makes sense for us. Okay. So look, we could do a flux integral without ever even needing to do a, what's it called? Parameterization and doing all those horrible steps. And I lost my page count, so this is page 5. Okay. Okay, I'm gonna save this for later because I promised I was gonna stick with the divergency stuff. So I'm gonna save that for later. I'm gonna show you a kind of a cool physicsy or engineering application. So if you're interested in engineering or just, I mean, this is I think this is interesting for anybody, but here we go. Let me show you. This is a nice application. So application of divergence theorem. I just thought of this last night, and it was like, oh, this is really actually pretty. So pretend you've got a river or like one of the bayous in Houston or anything. You know, the river, it's got water moving through it, and you could use a vector field to model the velocity of the water quite nicely. Okay, so let me draw kind of a chunk of a river. So let me use blue. I like blue. So so a river kind of flows like this for a little bit. And let's say the river gets really wide at some point. Okay. Okay, so what I'll have is I'll have a vector field. I'll explain what all this is. So I've got a vector field in a solid region. The solid region is this sort of weird looking thing. It's a river, and I've taken 2 cross sections. So over here, the river is, I'm going to call this S1, and I've taken like a perpendicular slice, like perpendicular slice of the river at S1, and over here, that's another perpendicular slice of the river. I'm going to call it S2. Okay, so now here's the top of the river. Okay, that's like the face of the water. So the top is like the, I'll call this S3. S3 is sort of like the, what I want to say, the water level, the surface of the river. Surface of river. And down here is sort of like the bottom piece, is that one last bottom edge. I'm going to just use it right here. I'll call that S4. And what do I want to say? I want to call that like the ground level. Like that's kind of where the water meets or interacts with the soil beneath, or the concrete if you're on a Houston bayou. So this is S4. This is the like ground surface. Okay, so the surface of the river is like water meets air. Ground surface is water meets ground. Okay, I'm getting crazy. Ground. And then this, I'm actually going to call this vector field, I'm going to call it W. So that's W. That's a vector field, W of maybe X, Y, Z for water. And this models fluid velocity. If you don't know what that means, I just really think it's directing how the water's flowing at that point. So you can see that the water is really going to be kind of coming out of the surface. Maybe even it's not coming out perpendicularly. Maybe the water's kind of moving around a little bit, but it's certainly kind of coming out of the surface on the average, and it's coming into this surface over here. So one thing that physicists, engineers like to assume all the time is when you have a fluid velocity, they'll assume that the fluid is something called incompressible. So This is an assumption that fluids are something called incompressible. And that just kind of means it's like you would never have water that kind of all starts squeezing into one spot. You really can't squeeze water is the idea. And the idea, like what this means right here is just that the divergence is 0. So the i.e. the divergence of W is 0. Okay, so now I'm gonna be able to show you that the flux through S2 is actually equal to the flux through S1. So claim, oh, I gotta tell you the normal vectors. So I'm gonna say this is, I'll do them all in red. So this is N2, this is N1. Up here, I'll use this is N3. We'll use this later. This is kind of less important. This is N4. Okay. So what I want to claim, I'm actually going to prove this to you. I'm going to claim that the flux integral over S1 V dot N dA is equal to the flux over S2 V dot N, N1, N2 dA. Basically telling you that like, because your fluid's incompressible, like at any slice, you're going to have the same amount of water flowing at any spot. Like, it would be weird if it was moving really quickly. How do I want to say this? Yeah. Okay, this is kind of what I want to say. This is what I'll say. I won't say too much. Another thing that means is if you believe this, if that's true, if this claim down here is true, then that means on average, if I look at this surface, then the water vectors are probably a little bit smaller over here because I got a lot of surface area. I mean, if the purple vectors were huge and my surface area S2, because my S2 is bigger than my S1, then I would have a lot of flux over here comparatively over here. Now that means that over here, my water is probably moving pretty quickly, which is agreeing with what we probably intuitively understand, that the river is going to move faster where it's pinched, or the water moves faster when it's shallower, you know, and on the right, and when it's lower and deeper, you know, as a river spills into a lake, it moves slower through the lake. This is just kind of what I'm trying to say. So to prove this, we'll use divergence theorem. I don't like purple, I'll use black for a second. Okay. So let's use, so this is actually proof. Okay. Use divergence theorem. So I'm going to say let omega be the 3D solid region, like contained on the inside. So then, okay, I'll put this on pause. So we have a question: how does the water being incompressible lead you to divergence of the? So a question that's in the comments is that that's just those are just what do I want to say? I want to say that that's an assumption that architects and engineers will place on fluids. I'm just gonna say that it's a really common notation that they'll use. Just maybe for an intuitive purposes, know that you wouldn't really see. Let me zoom. I'm gonna zoom in. Like, you wouldn't see one of these radially expanding things as a water flow, because like, where would the water be coming from? You would need to like be piping it in from the center. This is something that has positive divergence, and I'm saying that kind of doesn't really model how water would work unless you were artificially like pumping water into the center. Then it'd be flowing out. But typically water moving exhibits no divergence, because like, if this helps you out, it's like conservation of matter. Divergence is telling you how much matter is being created or destroyed, and physicists say that doesn't happen. So that's just think of it as an assumption. Just think of divergence equals 0 is an assumption that, okay, as an assumption that architects will use. So let's come back. So now omega is the 3D solid region bounded on the inside. So let's figure out how these orientations work. So this means that the boundary of S is going to be, okay, is going to be, well, we'll definitely have a positive copy of S2, comma, N2. That means like the N2 is really pointing outwards. Same thing with n3. The n3 is pointing outwards, so that's positive with respect to the inside. So plus s3 n3 plus s4 n4, because again, if you look at that bottom layer, the n4 is pointing outwards. But the only one that's different is the one on the left. On the one on the left, n1 is pointing inwards, so to correct it, I need to flip it outwards. So minus s1 comma n1. Okay, I want to save some room, so I'll just make this a little smaller. And you can maybe see where I'm going to go with this. Now that I have this data, I can set up my divergence theorem. So now divergence theorem tells us that the triple integral of the divergence on the inside, okay, this is going to equal the flux on the outside, and the flux has 4 components. So I'll go ahead and I'll write them all out. Double integral, double integral, double integral, double integral. I'll do S1, S2, S3, S4, v dot n1, v dot n2, v dot n3, v dot n4. These are 4 flux integrals, so we got to do it over A. Now I got to do the sign. So 2, 3, and 4 are all positive. Okay, so I've got a question. So why did you add a minus sign to S1? I'll say that in a second. So that minus sign that Christopher is asking right now is manifest in this piece right here. So the reason why is because a surface is going to be oriented positively if the normal is pointing outwards from the insides. But if you look at the picture over here, our red vector n is not pointing outwards, it's pointing inwards. So to correct that, I've got to put in a minus sign. In fact, let me, if it helps, I don't know if this algebra makes sense. Okay, I could say plus with a minus, because now I know minus n1 is positively oriented. I could actually do plus minus n1 on the inside, but it doesn't quite matter. So I'll undo those 2 last things I did. Okay, so we're almost done. We're almost done because a whole bunch of these things are 0. So we assume that the divergence of V is 0. So this is 0. Let's look at S3 and S4. Let's look at V dot n3. So you can already see that's going to be 0 because I'm going to zoom in on the picture. I'm going to show you why it's 0. I'm zooming in up 3 and zooming in up here, and I have a V, and that's always going to be orthogonal to the normal. Like, you're not going to have water like splashing out of the surface. At least you're not going to model it that way unless it's like a fish. But I mean, the water is moving horizontally, so that's going to be 0. So that's always 0. And same thing, the water on the ground layer down here is going to be orthogonal to the Earth. It's going to move tangentially to the Earth, so that's 0. And you can kind of see what all this is going to happen. That's 0, that's 0. So if I rearrange this whole equation, I get what we were trying to show. S1 V dot N1 dA is equal to S2. I moved 1 to the negative side. I moved the negative thing to the left. S2 V dot N2 dA. Okay, which is what we were trying to show. QED. That means what was remained to show has been shown. Okay, so that's really showing you that the flow on the left side is going to equal the flow on the right side, meaning it's probably moving, the water is moving slower on the right. Okay, that's a cool little application of Divergence Theorem. Okay. So there's one thing that I don't have time for, so I'll save that for tomorrow, for Friday. I think it's kind of cool, but I want to change gears. So I'm not going to talk about divergence theorem. I'm going to talk about the last problem that appeared on the homework that you turned in this weekend or on last Friday. So okay, here is the deal. The deal was we have this vector field that we've worked with so many times. It was negative y over x squared plus y squared, comma x over x squared plus y squared. And we know that this thing has a singularity at the origin. So the whole point of this example was the following. So I'm going to have two curves. I'm going to have, this is going to be C1, and this is going to be some C2. Okay, so I want to compare and contrast what happens with C1 and C2 a little bit differently. So let's look over here at C1. Let's look at C2. So on one hand, I see that the single integral, the work integral over C1 is 2 pi. There are a couple different ways that you can see that. So why? There are two ways. One, you can just actually parameterize the thing, and it's not that bad to actually compute. So actually parameterize and get that using cosine of t, sine of t, and then you actually get 2 pi. So you just roll up your sleeves, you do it, you get a sine squared plus a cosine squared over it from 0 to 2 pi. That's how that works. You also believe that you're going to get a positive number, because I'll draw the vector field in purple right here. This vector field actually is always doing this. So, it makes sense that at every spot you're making not just an acute angle, like a zero angle. So you're adding up a positive number along your entire curve, along that green curve. Okay, so that's one way you could see it. A second way you could see it, method 2, is you could actually use the fundamental theorem of calculus. You can parse up the domain. You can say that the curve goes through this piece plus, okay, I gotta be really careful with how I write this, okay, plus this piece. Basically, you can show that there are 4 different spots where it racks up an angle of pi halves. Okay. Hopefully, I really hope that was clear in that example, that you could break the curve up into these 4 pieces, and in these 4 pieces there was this arctan. Arctan is measuring angle theta, and so you're really adding up these 4 pieces of theta using fundamental theorem of calculus. Method 2, using fundamental theorem of calculus, you add up pi over 2 4 times by looking at like arctan, basically it's like theta 1 minus theta 0 4 times. Okay, so here are 2 ways you can see that. What you can't use, you cannot use Stokes' theorem here. You can't use Stokes' theorem because there's a singularity is enclosed by C1. Okay, so on the other hand, let's look at S2 or C2. So C2, you can see this in many different ways, that the single integral over C2 v dot t ds is going to be equal to 0. Okay, and so one reason why, you can use Stokes' theorem, because there is no singularity contained on the inside. So because there's no singularity, you can say that the single integral, C2 v dot t ds, just this thing, equals the double integral of the curl on the inside. And you can show that this is 0, so the full thing is 0. Okay, and then there's another way you can see that this is 0. So method 2, you can see it's 0 because I have a closed curve. It starts and ends at A and B, and it completely is contained in the domain of the function f. So C contained in domain of f of x, y, which is arctan of y over x, because the domain of this function are these 2 half planes. So thus, I'm just about done. So thus, by the fundamental theorem of calculus, the work integral over C v dot t ds will then be equal, you can then say it's equal to f of A minus f of B, or f of B minus f of A. But those are the same number, so that's 0. So basically, yeah, this vector field is conservative on that side. Okay, so that's something I wanted to say, and I have a couple more things that I'll say on Friday, and I'll stop my recording right now. Okay.